Hi everyone, and welcome back to another CBRG session. Today we'll be talking about how to handle strings in R. To quote Hadley Wickham, strings are not glamorous or high profile, but it's important to know how to deal with them. So as usual, if you have a project associated with these meetups, you can open that up, or you can just open up RStudio, and you go into the console. As usual, we type in remotes install underscore github dupe cct slash cbrg force equals true to install the package. Um, hmm. Oh, and after you've installed the package, load it with library cbrg, and then we can launch the RMD for today's meetup with launch project in 16. This is the 16th meetup. All okay? Cool. All right. And then as once you have this opened, it's a nice idea to save it. So to do that, you have to go save as, and then you navigate to the directory that has this project, if you do have a project associated with it. This way, if you make any changes to this, it gets saved in your project directory. So this is 16, project number 16. And unlike previous sessions, we won't be using that many packages this week, just because we're just handling this, focusing on this one aspect. And so the packages we'll be using are really just the tidyverse and this additional package called Tidy Biology, developed by Matt Hershey for his Tidy Biology course. We will be using a data set that contains proteins, protein information. And so the first thing to do is to run the setup chunk, and that will install any packages that need to be installed and load them. So if that's all okay, just move on to what strings are. So a string in R is anything within quotation marks. So I am a string is a string. And much of this walkthrough, although it's hopefully relevant to biological data analysis, has been modeled on the strings chapter of Hadley Wickham's Art for Data Science book, which is freely available online. And here's a link to it. And we'll mostly be making use of the stringer package, which is within the tidyverse. And there's really nice documentation on this package that can be found at this link on line 63. And finally, as with all of the packages in tidyverse, there's a cheat sheet. And that's a really useful resource, especially for string manipulation, just because it's kind of its own language. So to begin, we'll just start with one example and look at some really simple applications of string manipulation, and then we'll move on to more relevant things. So if we go to line 71, there's this one string here. So you can see it's just a sequence of amino acids. And we can assign the sequence to an object called string. And that's what we'll use to for this simple example. So if we go to line 73, you see the question, how many amino acids are in this sequence? Like a natural thing to do is to just look at the length of the string. If you run that, though, you get 1, because the length function just thinks that this is one thing, which it is. But to get the number of individual characters, we can use our first function from the stringer package called str underscore length. So a good thing about the stringer package is almost all the functions in it start with str, if not all of them. And if we do str underscore length, we get string, we get 31, which looks like the number of amino acids in the string. And this question, why do these functions give different answers? So we do question mark str underscore length. It goes into what this function does. So I think the default is if you give it one contiguous string like this, it will look at the individual elements. So now moving on to something a little bit more useful. So on line 79, there's a question, how many lysines does this sequence contain? So for that, we can use this function called str underscore count. The way that works is you give it the name of the object that contains your string. So in this case, it's just string itself. And in this case, we can do what's known as literal matching. We are literally trying to count the number of L's in this string. So you can just give it capital L. If we run that, we get 5. So there are 5 lysines in the string. It's a pretty simple example. One thing that Hadley Wickham does in his book is he makes use of this function called str underscore view or str underscore view underscore all. And this is not typically a function that people use for, or at least I use for like the data science part or the analysis part, but I do it to make sense of what's going on. So if we run that on line 81, you see what this what the code is done. You should be able to see the sequence along with all the L's highlighted. So they're in little gray squares. So you know that you are actually counting the number of lysines. You can actually see that. That's maybe the simplest example of handling a string in R. If we go to line 83, the question is, how many times do 2 consecutive alanines occur in the sequence? Again, we can just do string count, string, and then we can just do AA. And if we run that, we get 1. So it's just 2 consecutive alanines. And again, if we do str underscore view underscore all, you see that the 2 alanines are towards the end of this sequence. So this is string count, str count. It just counts the number of matches that are in your string. We can move on to the next function. So to answer this question on 87, does the sequence contain a proline followed by a valine followed by a threonine? So this function, the function that we can use is a thing called str underscore detect. And str detect produces a Boolean, true or false. So if we do string, and we're looking for a P followed by a V followed by a T. If we run that, we get a true. So a PVT is somewhere in our sequence. And if we run the str underscore view on this, we can see that this is a small sequence, so it's easy to see what's going on. This PVT occurs only once. So the final question in this simple intro is, does the sequence contain a tryptophan followed by any amino acid and then a valine? This is embarrassing, but tryptophan's W, right? Okay. So we do str underscore detect string. And so we know the first one we want is a W. The last one we want is a V. But then it says followed by any amino acid. So the middle amino acid is anything. So we can use what's known as a wildcard character. So that's dot. So the thing with handling strings, and we'll get into this in more detail later on, is that just doing literal matching like you would in a Word doc if you run Control F or Command F is useful but limited. So we can't, or at least as far as I'm aware, we can't really use Word to do this kind of, or I haven't used Word to do this kind of more complex matching. So this is the simplest example of this more complex matching. We can use these special characters. So if we do w.v, Stringer is not literally looking for a W followed by a dot followed by a V. It's looking for a W followed by anything followed by a V. And so if we run that, it's true. There is some subsequence here that has a tryptophan followed by something followed by a valine. And to see what that is, again, we can do the str view all. If we're curious to see what that middle amino acid is. And we see that it is G, glycine, which is cool.
It's a stupid question.
Yeah.
If you're actually looking for a dot in something.
Great question. That's not a stupid question. And that's actually, I hesitate to bring that up because that's called escaping, I believe. That's the term for that. But this wildcard character is one of many so-called meta characters. And so that's the part where this gets a little bit challenging. And the cheat sheet that I mentioned, it does a really good job of describing these different meta characters. So there's a way to tell R to literally look for a dot. and we'll look at that a little bit later. But that's not a stupid question by any means. So line 99. So now this is just handling one object. But typically what we do is we do work with data frames when we're doing any kind of actual data analysis. So for that, we'll be using this data frame called proteins from Matt's Teddy Biology package. So first quest on line 99, it says to take a look at the proteins data frame. So many ways to do this. I'm going to use view. I like that function. So if we do view proteins, we can see that it is a huge data frame. It contains around 20,000 proteins. And importantly, there's one of typically the data frames, at least I work with, mostly have numeric data. This is one of the rare ones that mostly has text data, so it's perfect for today. So you can see it has like gene names, protein names, uniprot IDs, sequence information. So the first question, which is on 102, line 102, is how would you create a new data frame that only contains proteins that contain the RCP.L motif? So again, the dot means wildcard, anything. So we take proteins, and then we can pipe it into, what we can do here is to create a new data frame, we can use the str detect function in combination with filter. Because str detect produces a bunch of trues and falses, which is what we need for filter. Because a filter will keep any row that corresponds to a true and get rid of any row that corresponds to a false. So we do filter, and within that we do str underscore detect. We have to give it the name of the variable so that contains the sequence information, which is, I think, just called sequence. Let me double check. Yeah, it's just sequence. And then we can do what we did previously, just give it the rcp.l. And I'm not going to save this data frame, I'm just going to run it. And you can see in the console, it gives you the resulting data frame, and that only has 46 rows. So there are only 46 proteins in the entire proteome, human proteome, that have this motif. Pretty simple. So on line 106, it's so that's a simple example, but it's I think a useful one of showing how we use or can use stringer with the rest of with dplyr functions. And on line 106, it says to identify proteins that contain the ebox motif, which is CA anything TG. So create a new column called ebox that contains a true if a sequence has this motif and a false otherwise. So to do that, we can go proteins. So to create a new column, we can now use the mutate function. And it says to call a new column ebox, and that's equal to str detect sequence, and then the ebox motif is ca dot tg. And if we run this, again, I'm not going to save the output. If you look at the console, you now see a new column at the end called ebox that has trues and falses, depending on whether or not that protein contains an ebox or not. This by itself is not hugely useful, but this can be the first in a longer string that produces something more useful. So that's on line 110. What are the mean protein lengths for proteins that contain an ebox versus proteins that do not? So what we can do is we can just copy paste this, and then we can group by ebox. So this will group on either true or false. And we can summarize, and we can say length is equal to mean, and there's a variable in this data frame called length. So length is equal to mean length. And if we run that, you can now see this is potentially something useful. Turns out proteins that do have an ebox on average are much longer than proteins that do not have an ebox, which for an expert on eboxes, that might be obvious, and someone who's not, this might lead to some potential insight. So that's a quick fire overview of stringer and dplyr. Any questions? All right. So now we're going to move on to this thing called regular expressions. So regular expressions are kind of their own language, and it's a way of handling more complex string cases. So we've already used an example of regular expressions, and that's this dot dot business. There's a lot more. So what's a regular expression? So Wikipedia defines it as a short. So regular expressions are also referred to as regex or regex or regexp, and it's a sequence of characters that specifies a search pattern in text. And regular expressions are independent of R. You can use them in Python, Bash, whatever language. And so there's a really nice and brief, it's like a 30-minute introduction to regular expressions by Roger Peng. And that is about regular expressions just as an independent concept. So before we get on to some examples of some simple regular expressions, for these examples, we'll use just two very simple data frames so that we can see what's going on. And we can build those data frames on the fly. So if we go to line 127, we'll make a much smaller data frame that contains information on just 3 human proteins. And if you've not seen this, this is, if you ever want to make a data frame, probably the easiest thing to do is to just download it or use Excel or something like that. But if you wanted to do it completely in R, you can use this function called Tibble. And then you give the names of the columns you want your data frame or Tibble to have, and then that's equal to the entries that it contains. This is really easy to do when you have a super simple data frame, but for bigger data frames, it's a little bit more challenging. So we have proteins underscore small. You can take a look at that. We can see that it just contains 3 rows, 2 columns. And similarly, we'll make another one called my experiment. When we take a look at that, that's a little bit bigger. It has 2 columns, but 6 rows. And this is supposed to kind of simulate what a quote-unquote real experiment would look like. You can see we have 3 controls and 3 treateds. And we'll use both of these in this section. So on line 137, it says use protein underscore small, that data frame, for the following examples. So only keep proteins whose name begins with an A. So once again, we can do protein underscore small, and we filter. We can use a string detect function, and the name is protein underscore names. And we only want to keep the proteins that start with an A, and you can see that that's just the first 2 proteins. Now if I go ahead and just do this, and look at the resulting data frame, nothing is changed. And that's because if you just put in like A, it's going to look, if it sees an A anywhere in the string, it will keep it. We want it to start with an A, and to do that, we can use this meta character. It's called a caret, or the power symbol, and we put that before the thing that we want to be at the front of our string. So if we do caret A and run this, we now get an output that just has 2 rows. And to show you, just to confirm what this caret is doing, we can use string view. Go to line 142. If we just do A, you can see that all 3 entries of protein names, they have the A's highlighted. So all 3 will be selected. But if we do 143, you can see that the caret A is only matching to the first A. And then there's a next natural question: what if my string actually has a caret? How do I literally search for it? That's related to the literally searching for the period. So just a couple of other examples before we move on to the more advanced stuff. So 145 is remove underscore human from protein names from the protein small data frame. I put this example here because we frequently, when we download data frames, I find that you get this appended to the protein or gene name is underscore mouse or underscore human, which is great if you have a mixture of human and other species, but not so great if you just have, for example, human. So that's pretty, for this one, we'll be using a new function called str underscore replace. So this is all nested within this mutate function. But if we just look at looking at it from inside out, if we look at str, how str replace works, it takes in an entry, which is the name of the relevant column, then the pattern, which is a literal in this case. You're literally looking for underscore human, followed by what you want to replace it with. And if you want to replace it with nothing, you just do quotation marks. So this is, it's kind of silly. It's like so replacing with nothing is equivalent to erasing it. So if we run that and we look at protein underscore small, we now see that it still contains, oh, that's strange. Oh, I'm sorry. We have assigned it to a new column called gene underscore name. So you see there, those entries don't have underscore human. So that's how str replace works. And then one more example of this. So the reason I made this my underscore experiment data frame is oftentimes, especially when you're entering stuff by hand, like you can call things like for these controls, like some of them, like one is lowercase, all lowercase, one starts with a capital C. And this is typically not an issue if you're just in Excel or something like that. But the minute you start to bring it into R, obviously R sees a lowercase control and an uppercase control as two different things, but they mean the same thing. So one's really simple way to, so Stringer, in addition to, so regular expressions can get pretty complicated, but fortunately Stringer itself has a bunch of simpler functions that are specifically designed to do these one-off things. So if I wanted to make all of these lowercase, there's a function called str2lower. And so the same thing, you can do my experiment, pipe that into a mutate, and I just want to override my sample, so I do str2lower, and unlike the previous str functions we've looked at, this just takes in the name of the variable, and it will make everything in that variable lowercase. So if we run this and take a look at my underscore experiment, we now see this looks a lot neater. And also, like while it might be relevant to have these numbers that follow the like controls and treateds, from a like statistical perspective, if they're all truly independent, they're all a control. Control one is not. It will give the impression that control one is related to treated one. But if they're unpaired, you want to remove the numbers. How do you do that? One simple way is, all right, so we can do my experiment, pipe that into, so it says to create a new column called condition that contains the sample entries with the numbers removed. So we do mutate condition is equal to str. There are a few ways of doing this. We can just do str replace, give it the name of the variable, so it's sample, and then we can look to remove any digits. So we'll just do this. So let me run this example and then go through what it means. So again, we're using str underscore replace. But the thing we're replacing, the way to tell Stringer to detect a number, we can use this, again, this special notation. And this is an example from, you'll find this in the Stringer cheat sheet. So it's open close square brackets, and within it's colon, digit, colon. And there are other examples where if you wanted to remove, if there were punctuation marks that you wanted to remove, it looks similar to this, except instead of digit, it is punct. So that's the kind of unfortunate thing. There's this whole additional vocabulary to learn. Fortunately, for a lot of the more complicated examples, there's typically a solution on Stack Overflow. So if you really don't want to understand how this stuff works, someone's probably found a solution. I have an example of a simpler way of doing this that is now escaping my mind, but this is one way of removing the number. There are others. Any questions? Cool. All right, so now for the like advanced. So the point I guess that can be made here is just with this, along with other functions in the Stringer package, there's a lot that you can do that's pretty straightforward. But eventually you will come across examples where there's no getting around using some more complicated regular expressions. So I asked Paul to give me some real life complicated but real life examples. And he gave me a few, but I've only taken this one. And so we go to line 163. Again, we're going to move back to just looking at a few examples, so not in the context of a data frame, just a few examples so that we can see what's going on. So on line 163, we make this character vector called gene underscore names. So if I run that and then just run gene underscore names in the console, you now see that we have all of these gene names. But in front of all of these gene names are these parentheses with some numbers in them. So so one question is, how would you get rid of these parentheses and the numbers in them and just keep the gene name? So this is a little bit tricky because there's a lot going on. You want to first get rid of the space between the end of your gene name and the open parentheses, with the parentheses. You want to get rid of the parentheses themselves, and you want to get rid of what's inside the parentheses. But it's a little bit tricky because what's inside the parentheses is not of the same length. So in the first example, there's just one number. In the second example, there's 5 numbers. So there are a few ways of doing it. I'll show you Paul's way, which is the most robust, bulletproof way, and then I'll show you some hacks around it that work for this example, but might land you in trouble for... It's easy for this because we just have, 10 genes, so it's easy to see the output. But if we had like 20,000 genes, going the more robust route is always better. So having said that, we'll start with the most difficult first and then move on to the simpler ones. So line 165 says to remove white spaces, the parenthesis, and everything in the parenthesis. So we can take this gene names and then we can pipe it into string replace. So previously, we just put everything within the string replace function. Here we're piping, or Paul piped it in so that it's very clear, or makes it more clear what's going on inside the string replace. So if we look at the string, what's inside the string replace, as we've seen previously, actually we just hover, no, that doesn't work. What we have is we have the pattern that we want to replace, comma, the thing we want to replace it with. So the thing we want to replace it with is simple enough, just quotation marks, meaning that we want to replace it with we want to nullify it. What's more complicated is the pattern itself. So starting from left to right, the first thing we want to get rid of is the space. So the way to denote a space in Stringer is to do \\s. Why is it this? I don't know. I don't know who made this choice, but this /s is universal to any kind of regular expression. Why is it /s? Again, there's a lot to that, but the good thing is the cheat sheet, if you just look at space, like I want to match a space, it will give you next to it /s. That's fine. Now, there's an asterisk that follows the s. And what that means is I want you, so for example, if we go back to gene names and I put an additional space after G for the first gene, we want our search pattern to be robust to the length of the space. So it could be one space, multiple spaces. That's what this asterisk is telling R. It's saying basically 0 or more spaces. That's the pattern I want you to detect. So that's the spaces business. The next is the open parentheses. Now, Bev asked the question of like, how do you get rid of a dot? Like, how do you literally say I want a dot? You do // dot. So the problem with the open parentheses is they have their own meaning within a string. So if you literally want a parentheses, you do the same thing, // parentheses, open parentheses. So we're now up to, so we've taken into account the space and the open brackets. Now to deal with what's inside the brackets is a little more tricky, and that's inside these square brackets. So what this means, so the square brackets, and inside you see caret // caret / close brackets. What's a little confusing is, so if we just look at the // close brackets, that means we're looking for a close bracket. The caret means, within square brackets, means you negate the thing that follows it. Now, this is extra confusing because in a previous context, when we don't have the square brackets, so if we go back to line 143, if you just use caret, it has a different meaning. There it means I want you to look for all the strings that contain this, in this case, A, at the start of them. But if you put the caret within these square brackets, it becomes like the exclamation mark. It's a negate. I don't know why this is, but that's the case. So what we're telling are, and then the square brackets are followed by a plus. So that accounts for the one or more elements that could be within our parentheses. So what this whole block is telling us is look for anything within the parentheses that is not a closing parenthesis. That's what that means. And then, so that's the most challenging part of this pattern. And the final thing is, since the thing we want to get rid of ends with the close parentheses, we do / close parentheses. And that's all there is to it. And so if we run that 166, we get this very clean output. Now, just to show you what would happen if I were to remove, for example, the // asterisk, and we run that, we see that we get almost what we want, but it still retains that annoying space. So I think that, like with a lot of these things, like when you have, for example, lots of tidyverse code chained together or ggplot code, the best thing to do is just go through it line by line, commenting out code just to see how you break it. I think with this, the equivalent is to remove parts of the pattern and see what are you matching with. So this /dot business or the / special character business, I think that's worth getting into. So if we go to line 170, it says all special characters must be preceded by a slash. And so the example is, how would you detect only the first element of this vector? So this is using now another hopefully simple example. So we go to line 173. If we create this character vector, we see that it contains two elements. One that has a string of AB dot, and the other that has ABC. So if you just wanted the first element, a rational thing would be to search for anything that contains a dot. So what happens if we do str detect A and then just the dot? If we run that, we're detecting both. Because in this case, just putting the dot means that you're looking for anything. And by definition, both of these entries contain anything. So, but if we wanted to literally look for a dot, we'd go to line 178, and you do this / dot. If we run that, now we see a true only for the first element and a false for the second. What happens if we just do / dot? We get an error. And that's a little bit beyond me, because that's the weirdness of not just regular expressions, but also how strings work in R. So an easy thing to remember is just to put that additional slash, and then everything else is fine. So that was using, so 167, line 167, as I said, I think is the most robust way of doing this. But now we'll take a look at some simpler ways of doing, in this case, the same thing. So line 181 is, it says, on 180, it says to remove everything after a white space, including the white space. So you can see here, this is much simpler. Instead of, oh, and it's a new function. Instead of using str replace, there's a dedicated function for removing things. It's just called str_remove. And this is a much simpler example version of the previous one. It's // meaning we're looking for a space, followed by a dot, meaning followed by anything. And the asterisk says that that anything can be multiple anythings. So it takes into account the variable length of objects, of things that are after the space. So if we run that, we get the same output as before. So this is a much simpler way of doing the previous thing, except the previous one was really, it's this, the string pattern. If someone were to read this, it makes it clear to them exactly what your thought process was. I want to get rid of the space, the parentheses, and everything inside. This one on line 182 just says, I want to get rid of the space and everything after, which is equivalent, but is less precise. And then line 184 up to 185 shows the simplest example. It says compute the start position and the end position of the first word of the string using a white space as a separator between words by default. Oh, that's what the word, there's a function called word within stringer that if you have, so in this case, we go back up here to gene names, we look at the first gene name. If you gave R A1BG space something, in this case, parentheses 1, R will read that as two words. And so what the word function does, or the word function will read that as two separate words. The word function takes the first, what it considers to be the word, which in this case is just the gene name, and then gets rid of everything else. So to see how that works on a simple example, 188, if we give these two gene names followed by a space, that's the important thing, to the word function, if we run it, it just keeps the first quote-unquote word. So to see how that works on gene names, we can do gene names, pipe that into Word, and then we don't have to give it any input. And if we run that, we get the same as the previous, much more complicated stuff. So the good thing with Stringer is it was intentionally, I believe, built for people who didn't want to fuss around with complicated regular expressions for as long as they can. And so they've made a lot of these kind of like single purpose functions for that reason. And so Paul has this thing here about kind of the pitfalls of Word and how it's actually working. So on line 192, it's demonstration that this function is using a white space as a separator between words by default. That doesn't have to be the case. You can specify what the separator is. So he gives the example of if we do word, gene names, and we specify that the separator is 1, we can see, if we go back to gene names, a lot of these genes, well, some of them have a 1, some of them don't. So we can see what happens when we do sep equals 1. And we get this output, which is keeping everything before a 1, if that string actually has a 1. And if that string doesn't have a 1, Word is not doing anything to it. So this is just something to know, because it isn't obvious when you just look at the word function that it's separating based on spaces. And I think that's useful. So that's just one example of a complicated regular expression. Any questions? Cool. That's kind of so we could spend a long time just going through all possible useful examples of Stringer, which I think actually would be a good use of time. But we're going to end the Stringer application to variable information, that part now. And then I thought I would just include this bit here about we can also apply Stringer and regular expressions to any text data, other text data. So for example, column names. We can apply these same functions to column names. It's not that it's a little trickier. We just have to do something slightly different. So for that, I'm just going to use this example that I'm calling typical Excel, just because, and if we run that, line 201, and take a look at this resulting data frame, the reason I call it typical Excel is it's really common to have column names, variable names, have spaces in them. Like this is a very natural thing, and not just for Excel, actually. You see this in databases and things like that. But as you know, when we are coding, and if there's a space in a name, that can be problematic. So line 205, why are the column names of this data frame problematic? Well, if we were to filter, for example, let's say we just wanted to keep the row that contains gene A1BG, you do typical Excel, pipe that into filter, gene names equals this. Of course, you get a mistake because R doesn't see the gene space names as one object. So one way to get around it that is not so nice is to put backticks within backticks, and that fixes this error. That's not so great because now you're just adding more messiness to your code. Backticks in code just don't look nice. So one really quick way to do this, and this is oftentimes you'll see people use this function at the very start when they're importing a data frame, is to use this function called clean names. And this is from another package called janitor. And so if we just take a look at typical Excel, this is what the column names look like. But if we pass this data frame through clean names, and we save it as an object called typical R, if we look at typical R and we compare with typical Excel, you see a few changes. One, it's detected where the spaces are and put an underscore. And two, this kind of uneven capital, uppercase, lowercase business, it takes care of that by making everything lowercase. And clean names has other parameters that allow you to control how you want the output to look like, but the default is something that most people, I think, agree is a good convention. So that's a really handy, nice function. Now, but there are other examples where column names have a dot between multiple words, and this is super common in like bioconductor stuff. So what if you then wanted to compare this with, or you wanted to prepare this for someone who was expecting dots to be in the names? So you had to, so if you go to line 202, that would require replacing the underscores with periods in the column names. So to do that, we can again, so line 213, we can use the string replace function. But here, since we want to access the column names, we do call names. So if we do call names on typical R, if we just run that in the console, you just get these two column names. And then we use string replace as usual. We give it the pattern that we want to detect. So that's the underscore. And then we give it the pattern we want to replace it with. That's a dot. This is potentially a little bit confusing because in this case, to replace it with a literal dot, you just give it a dot. You don't give it a / dot. And so if we just do copy paste the string replace part into the console, we get our cleaned names, column names. How do we assign those column names to, or replace the column names of typical R with these two? We have to make sure that we assign this again to the column names of typical R. To access the column names, you do call names of typical R. And so if we run line 213 and look at the typical R data frame, we now see that we have the clean names, but instead of underscores, we have periods. And that's kind of all I have for this session. Any questions or examples of things you've had to deal with strings? I know, sorry, it's on the spot.
That map gene IDs are nice initially when you download the raw file.
Okay.
And so each gene symbol is followed by a period, and then numbers representing some, designation of the gene, and then another period to end it.
Oh, so would that, so if I did like dep example is, what was an example?
Let's see.
Oh, you can just say the thing.
Oh, so it's like the gene symbol. So for example, I have mTOR here. So the gene symbol comes out as mTOR dot 2475 dot.
Oh, wow.
And it's like the number is different for each gene, in as far as the length of the characters of the number.
Right.
But what's shared for every gene is the dot before the number and the dot after.
So that makes things easier. So I think it's just, if I'm not mistaken, if we do, oh, sorry, that doesn't work. Yeah, Paul, can you tell me why that doesn't work?
bar dot like. Sorry.
Nice. So that's one solution.
Okay. Cool.
Oh, I see. Because if you do dot and then star, it's looking for dot followed by anything, which doesn't exist in this string. Got it. Got it. But if the example were mTOR dot 2475, and then you did it my way, the previous way, in that case, that still doesn't work. Oh, because I didn't assign. That still doesn't work. I'm confused about that.
So you want to remove only a dot?
If the dot and everything after it, if you have mtor dot 2475 dot, just gonna try something now. Huh. Okay, so I tried something that is probably not right, but it works. So if you do slash slash dot, and then you can use the digit thing that we looked at earlier, followed by a dot and then an asterisk. So what this is telling it is look for the first literal dot, then look for a number that follows that dot, followed by anything of variable length. But I'm sure there's a better answer. But the good thing is there's actually a dot dot in your case. So the solution there is to do Paul's thing of slash slash dot dot asterisk. And that works. Cool. I guess if there are no more questions, we can just end the session. Thanks for watching, and I guess see you in 2 weeks' time.